Hi, and welcome to another Hopper video. This one is about the OLED displays, the SSD1306s, and showing how you could do a sprite engine on these, for writing things like games, with using very little memory. And let me explain why. So continuing. This is a response to people showing interest in trying to write a game on this device of Anders Nielsberg's, the 6850 Ueno. This thing only has 128 bytes of RAM, and it's all in this interface chip, the Riot chip. So it has 128 bytes of RAM. And it's a bit of a challenge to do the graphics on this particular OLED display with only that much memory, because this is a write-only device. So once you've written a pixel to the device, you can't tell, where the pixels are lit and where they are not. Now, many of us who've done this for a while have taken advantage of the Adafruit libraries as a place to get started, even on other platforms. Lots of cut and paste. And the Adafruit libraries are very good, but they're also fairly generic, so that they only had to write one set of graphics functions that work everywhere. The way they deal with screens like this one that are write-only is they'll have a buffer on the microcontroller side. So they'll keep everything that you've drawn onto the screen in this buffer, and then just update the buffer to render the screen. Update the screen by rendering the buffer. Which sounds like a good solution. It's a pretty good solution if you've got a fast microcontroller. It's a little bit slow if you're using something like a 6502. But this idea falls apart when you only have 128 bytes of RAM, because you've got no room for the buffer, and let me show you why. For this particular screen, you've got 128 columns by 64 rows, and this is how they're arranged in memory on the device. They're in 8 pages. And so 128 by 64 gives you 4096 pixels, divided by 8 because that's bits, and then you'll get bytes. So that gets you 1K, 1024 bytes of memory required for this screen buffer. So that's just you can't have that kind of size buffer when you've got, a tiny device like this guy. It's not going to happen. So how do we deal with this? Well, this was a problem when people were writing games for these 6502 machines, or like the first Atari game machines, which did run on the 6507 and had very limited memory. And this is where the whole concept of sprites came from. So a sprite is just sort of an abbreviated way of keeping track of what is on the screen. If a font is really a sprite, so you keep one pattern for the A character, and you draw it multiple times on the screen, and then you keep track with the text buffer as to what's on the screen in which positions. So for a text buffer, you might have 5 columns by 8 rows, and that might be your text character, and you've got a pattern somewhere on your machine, and you only have to keep track of 1 byte for this whole 5 by 8. For all 40 of these pixels, you only have to keep track of the fact that in this text coordinate there's an A. So sprites work in a similar way, but they're evolved to have more functionality, like for example Z order, so you can have them on top of each other and they can slip in front and behind of each other, or you could do collision processing with them. You could build that into the sprites, so some sprites should be bad to hit and some should be okay to just run over. So like bushes in your scene, for example, you should be able to run over, but if you shoot the duck, it should hit the duck, whatever. All right, so with that little background on sprites, let's see what we've got. So I've got these little things running around here. Let me start them again. My random number, this is not a game, this is just a demo of how to do the sprites, so it's not very good in terms of they tend to, my random number generator is not that great, so they tend to cluster. Anyway, I've got these little sprites running around in circles, and they can run over the hollow sprites they can run over, and the solid ones, they can run into each other, go over each other. Let's see if I can get another better pattern. These are randomly generated, but my random number generator is not that great. Let's get another one. There we go, that's better. So you can see they're wandering around randomly, they're bouncing all over the place, and they go over other sprites, and this is being stored in, this scene here is being stored in 32 bytes. So not 1K, 32 bytes for this for what you're seeing in the demo. Let's go back and see how I did that. Okay, so in this memory arrangement, the smallest bit you can write to the screen is one of these vertical strips, which is a byte. So the problem is, if your sprite is smaller than this, and my sprites are 4x4, it means that when you write out this 4x4 sprite, you're going to wipe out the one above it if you don't keep track of what is there. So I do. So I keep track of where all my sprites are, and if you draw one sprite, it'll have to go and check if there's another one visible there and make sure it doesn't destroy it. So here's how our memory layout works. So in my code, I'm calling these guys cells as opposed to pixels. So, so that you can tell the difference between a cell and a pixel when you're looking at the code. So a cell is 4x4, and a pixel is one bit, right? And then to draw, and so the way my system works is the cells have to be on 4-bit boundaries to work. So you can't have one that's offset into a space. Much like when you're drawing text on a screen, the text has to be in cells usually to make a simple system. So to draw two of my sprites, two cells, you have to draw what I call a slot. So this is the smallest unit that gets drawn from my code. Okay, let's go and have a look at it. So here we are again. I can also do that without the noise going on the screen. There we go. And break out of that. Okay. I'm in the Hopper debugger right now, and I'm actually, if I lift this up, you'll see, I'm running on a microcontroller. I'm running on a Raspberry Pi Pico style device, right? And it's what I'm prototyping in, because optimally we want to get this into 6502 assembly. But 6502 assembly, to do a proof of concept of this nature, will be a lot of work. So it's much easier to first prove it in a high-level language, and Hopper is a great language to do that in, because it's essentially cross-platform when it comes to microcontrollers and 8-bit CPUs. And let's walk through quickly what my program does. So I've got it targeting the microcontroller right now. If I want to target the 6502, I change one line of code. I do have my OLED driver loaded up. I'm using that to initialize the display, and I'm using that to clear the screen, right? And that's all I'm doing with it. Once I've done that, I'm drawing with my sprite drawing routines. Okay, so I do have some tools. So if I right click on this, we go look at them. I've got a pretty bad random number generator, but I'm not writing a game, I'm just doing a demo, so I don't really care. We obviously need to put some more thought into random number generation. I'm sure there's a lot written on it. And then I've got three methods I've got here: initialize, render, and move. So let's go and have a look at initialize first. So I right click on that. It's in the sprites library. I can also just right click on that. Right. So here's how I define a sprite. I'm fitting each sprite into 2 bytes, into an unsigned integer in Hopper. So I've got an array of sprites here, array of uints, and the memory required to maintain the scene is 2 times the number of sprites. So I've got 16 sprites, and that means this is 32 bytes of memory which is used to maintain this scene. I've made some sample designs of my sprites. This is not very efficient. I could squeeze them into 2 bytes instead of 4, but it's a prototype. And these are constants, so once on the 6502 implementation, they'll be in the ROM, they won't be in RAM. Okay, let's see how I've defined sprites. I've broken my 16 bits down like this. So I need an x coordinate and a y coordinate, which are in cell locations. So the height of that screen is, oh, that's a typo. There we go. The height of the screen is 64 bits, 64 pixels, so 64 divided by 4. So you've got 0 to 15, you've got 16 Y locations for your cells, and similarly, you've got 32 X locations for your cells. So 5 bits for X, 4 bits for Y. Let's talk about Z. I don't think these things are going to get terribly complicated. So we've effectively got 3 Z order positions, which are 1, 2, and 3. Because 0 is a way to hide your sprite away without deleting it. To make an invisible sprite should you want to do that. And it's also a useful concept for the rendering to have invisible sprites, because I've actually got a blank sprite that I use. So if I am drawing, let's go and have a look. If I'm going to draw what I'm calling a slot, which is 2 of these, and one half of the slot does not have a sprite in it, that means I've got to draw an empty sprite there. So that's what I mean by it's useful to be able to, let's just do that again, no distraction. It's useful to have a blank sprite, and it's useful to have a Z order 0 mean draw the blank sprite, right? So what haven't we discussed? The sprite index, yes. So this is a bit over the top. You can have 16 different sprites, really just 15 sprites, because 0 is probably reserved for the blank sprite. So you could have 15 different sprites in your game. Probably not a bad idea. It's not a lot of memory to store, especially since each sprite will only take 2 bytes to store. Here I've got them stored in 4, but you could store them in 2 bytes, and they're in ROM. So okay, you could have up to 15 sprites. And then there's one final bit, which is the user bit, which you could use for anything you like in your game. And I use it to distinguish between a sprite that should be moved around and a sprite that should stand still. So I've got a solid block, a solid circle, and then the diamond is really a hollow circle and a hollow box. And my definition is that the solid ones move around and the hollow ones are standing still. But it's really, you could use it for collision detection as well, so that you don't, it's like a class of sprites without actually having to check for every little sprite that you can collide into. So you don't have to like run through a little if list of all 5 of these are bad things to hit, you're going to lose your, lose points. So instead you've got a little bit you can check in collision processing. Let's carry on. So now that you know how the sprite is structured, here, this is me randomly setting up sprites. So I'm running through a loop for my number of sprites, which is 16. And when I hit a maximum number of, I'm setting solid sprites for index 1 and index 2, which is, in my case, these solid ones are block and circle. So once I hit my limit of solids, I just go and look for another random one until I fill the rest of the space with hollow ones. And here I am building those bits. And then the output that you've seen to the serial console is just my diagnostics to show me what I've actually managed to build. So yeah, prototyping in Hopper, super easy. Yeah, again, you wouldn't do this in assembler with a switch statement. Well, actually, the switch statements from Hopper to Hopper ones are pretty good, but yeah, in assembly there is no switch statement. I mean, jump table or something. But so yeah, you can prototype very inefficiently. The point of this whole exercise was to prove that the memory required to maintain the scene was very small. Let's carry on. So now let's go back. So that was our initialize. Control backspace gets me back to my previous file. Then I cleared the screen, which is just using regular Hopper display driver stuff. And then I render the sprites. So let's look at rendering of sprites. So I don't render the screen, I render the sprites. So I step through 0 to number of sprites, I go get the sprite, and then when I get the sprite, I've got to pull its bits out. The first thing I'm going to do is check if it's visible or not. Then I'm going to go get the sprite index. Do I even use that? Don't even need that anymore. There we go. Actually, I'll just delete it. So all I need is the X and Y coordinates of the sprite that I want to draw. Actually, they're not the X and Y coordinates, cell X and cell Y, right? So comments like these are bad, when they don't say the right thing. And we can just say check if it's visible over there. I like the comments to stay up to date with what's going on. Right, there we go. All right, and then we render the cell at X and Y. So now what does it do? It rounds the Y down of the top cell, because you're going to render a slot and not a cell. You're going to render two sprites. So it rounds it down to get to this one, right? So we're rounding down to get to the top slot, and then we're going to get the index for the top slot and the index for the bottom slot. Well, we're going to see if there is a sprite present in the top slot and a sprite present in the bottom slot. So there's the top slot, and then the bottom slot, the purple one, is the +1, right? And it'll go and see if they're present, and this is a hopper function for it, and it returns two values. So the reference is the actual index, and the Boolean tells you whether there was something there or not. So if we go and look at that, right-clicked on it, it's going to loop through the sprites and see if any of their coordinates match the position we're talking about, and if so, it finds it. Then it checks if it's 0 or not. So if it finds one that's not 0, in other words, visible, so the found index default is 0, which is actually blank. And if it finds a non-blank one, it'll find the best C value, in other words, the one that's on top, the one that has the highest C value, and it'll tell you, it'll return what the index of the sprite is that it's found. So we control backspace, we go to where we were. So here we were, sprite present, sprite present. So if there is a sprite in either of these slots or both of these slots, then we're going to actually go and do some drawing. Otherwise, we're not going to draw. There's nothing to draw. So once we get to there, we go and get the sprite itself, which gets the data of the sprite. And then we render the slot. So that's rendering the cell, that's rendering the slot. And you can see the coordinates are now being translated from cell coordinates to pixel coordinates. And this is the code that actually talks to the device, via I2C, to the SSD1360 OLED device. So it's got to set it up with the coordinates in the page. This is how you calculate the coordinates in the page of the start of your slot. And then conveniently, you can draw 4 consecutive bytes with only setting up the coordinates once, and that's what this is. So it's looping around and drawing 4 consecutive 8-bit high slots. So the 1, 2, 3, 4. So like they draw like this, you know? Yeah. Okay. And for each of them, it's ORing the bottom sprite and the top sprite. And actually, oh yes, it's counterintuitive. The most significant bit. Let's see. Yeah, the most significant bit is at the bottom. Yeah. Right. So the bottom sprite has the bigger digit. It has the bigger values. My sprites are all symmetric right now, so you can't see if they're being drawn upside down or not. But once you start to draw non-symmetric sprites, you'll figure that out, and you'll change the way you draw your sprite, so it draws the right way up. Anyway, that's about it. That's where it's drawing. So, and then the only other thing I haven't shown is when I'm randomly moving them. So I'm looping forever and randomly moving them. Let's make this bigger again. So when we're moving them, the way you move a sprite, I think this is kind of key to writing a game. So I'm stepping through all of them because I'm going to move all of and I'm only moving the solid ones. So if it's solid, so that's the user bit that you could use for anything you liked, like you could use it for collision processing or something. I'm using it just to say I'm only moving. My demo is moving solid sprites, so I'm using that user bit to say move the solid sprites. Right, get the index of the sprite, get the Z coordinate. Is it visible? So if it's visible and I want to move it, that means I first have to hide it away. So I first have to draw it away. So the way I do that is I set it to invisible by setting its Z to 0, and I draw it in its current position. And what that'll do is it'll see that it's invisible and it'll draw a blank. And if that sprite cell is sharing its slot with an adjacent sprite, it'll draw the adjacent sprite as well, so it doesn't wipe the adjacent sprite out. And then I got some really convoluted code here for doing my random increment because of the way, I wanted to do signed integers so that I didn't have to mess with the -1, etc. And I want to do it in ints, not bytes, etc. So it is just really painful. So suffice it to say, I randomly choose between -1, 0, and +1, and add that to the current position to randomly move the sprite. And then if it goes off one of the edges of the screen, I just bounce it back in. But that's just moving it around. Once I've done that, I recreate the sprite from I've already stored its stuff. And I stored the Z as well, which I wiped out to 0 over here to make it invisible, but I just put it back. Now I put it back in its own Z position, and then I render it in its new position. There you go. So we can F5 here in the Hopper environment. Let's go and get our device. There we go. It's still showing the old one. So you can, in the Hopper debugger, this is why it's nice to prototype in this. We can put a breakpoint in here. All right, so a breakpoint. So let's put a breakpoint in when we move one, so we can actually see the moving around. And then I'll hit F5 to run until this point, generate some new sprites, and it's updated the screen, and we're sitting here and we're waiting to move one. So if we watch the screen, we should, and if I hit F5 here, we should see one of them move. There it goes. And as I click through, you can see them moving one by one. Yeah. And if you look in the debugger, I can see here, I've got all this local variable information here. Right now they're in hex, so there's the array of sprites. But you can watch them in decimal as well, so you can see where you are. So really good debugging environment. Anyhow, so this is how I prototyped the concept of, is it possible to, using the screen, maintain your scene of your game in as few bytes as possible. So you can maintain, with this design, you could make a sprite engine where you only need 2 bytes per sprite to maintain the scene. Now let's see what this looks like on the other device that I have here. So let's build for a 6502. That's how much effort it is to build for the 6502. Okay, so we've built for our other machine. And now we're going to have to go switch to that other machine. So I have a second machine here. So what is it? It's a breadboard version of my 6502 machine. Since this is what I'm doing while I'm waiting for my PCBs to arrive. Decide to write some code, and I have to unplug the power from the one board and plug the power into the other board. I'm using USB for power, and this has probably already got the demo on board, but we'll run it from here. So we'll build it again, and then you can see it's a lot slower, generating code, etc. And now we F5 to upload into the debugger. So it stops when I load it into the debugger. And now we can go put a breakpoint on render. And F5 to there. So it generates you can see it's a lot slower. And now we're going to render the screen. So I used the display method to clear. And now render the sprites. There they are. And now we're on the move. So if I press F10, it'll move. So on each one, it's moving all the solid ones. Okay, let's exit out of here. I don't know if this is it is optimized. Anyway, so that's showing how easy it is to take your prototype sample that's written in Hopper and prototype on your microcontroller and then get it running on your 6502. Anyway, if we control F5, we'll run outside the debugger in the Hopper monitor, and it should be slightly faster. There we go. They're moving around. Now, obviously, this this is it running inside Hopper, which is interpreted on a virtual machine. So obviously it's a lot slower than if you wrote it in, this is an 8 megahertz 6502. So if you're running it on a 1 megahertz 6507, but you'd written the same stuff in assembly, not in Hopper, I reckon it'll be plenty fast and it'll work just fine. Anyway, Control C out of there, I'll wrap up. So the sprites, how big is it? In terms of how much work is this? So the actual work here is checking if the sprite is present, is just a little comparison function. Moving the sprite is my random number thing, doesn't count. So the real code is the render, render cell, and render slot. And this is just a loop to render all the sprites. This is to render what's in a specific cell. So this is the code. That's it. It's basically these two methods amount to the sprite engine. Anyhow, let's get it running again, and then I'll fade out. So if I do port this to the 6502 to assembly, I'll do a follow-up video on that. But anyway, the concept's proven. It's been tested. You know how the layout of the memory works. You just do exactly what I've done, but just do it in 6502 assembly, and you'll have a little sprite engine running on the screen with very little memory use. Thanks for watching.